Hey y'all, welcome back. Today we're going to be reviewing Unit 8, which is all about exponential and logarithmic functions. Let's jump right into it. Number 1 says write in exponential form. So we're going to rewrite this logarithmic equation as an exponential one. So the base here is 3. The exponent, which is what the logarithm is. Remember, a logarithm is an exponent. We have 3 to the power of negative 2 equals 1/9. Which is true. When you're rewriting these as exponential equations, basically just look and make sure that the equation makes sense, right? And this is true. So log of 1 equals 0. The base here is going to be implied to be 10. This is known as the common log. So we're going to write this as 10 to the power of 0. Okay, the exponent is what the logarithm is, equals 1. Number 2, write in logarithmic form. We're doing the same thing, but just backwards here. So we're going to rewrite each of these in terms of logarithms. So here we can rewrite this statement as log base 5. Let's see, there we go. Log base 5 of 25 is 2. So this is saying that 5 to the second power is 25. For part B, we've got our base as Euler's number, and this is an approximation, so we want to make sure that we write our answer as an approximation and not as an equality. We're not going to write log base e, okay? Instead, we're going to write natural log, or ln, of 1097 is approximately 7. All right, so let's move on to number 3. Number 3 says, evaluate the following. So we're going to try to do this without a calculator. And so I just kind of want to guide you through how to evaluate these. So whenever you're evaluating a logarithm, remember, and I'm going to keep saying this over and over again, that a logarithm is an exponent. So we're looking for the exponent. In other words, in this case, we're saying 2 to what power is 64? Okay, so 2 to the 6th power is 64. So since 2 to the 6th power is 64, we can say that log base 2 of 64 is 6. Part B says log base 5 of 1. So again, here we're looking for the exponent. 5 to what power is 1? And so the answer here is going to be 0. 5 to the 0th power is 1. So this thing equals 0. 2 to what power is 1/4? Okay, so 1/4, another way to think about 1/4 is that it's 2 squared. So we can say that this is going to be 2 to the negative 2nd power is 1/4. So log base 2 of 1/4 is negative 2. Part D says the natural log of e to the 11th. So when you have the natural log, this is one of our special logarithms, where the base is implied, and it's implied to be Euler's number e. So in other words here, the base e to what power is equal to whatever's inside the parentheses here, which is e to the 11th power. And we can see, e to the 11th power is equal to the e to the 11th power. So that natural logarithm here, natural log of e to the 11th will equal 11. And one quick thing I want to mention here, if you ever notice you have a setup like this where the base of your logarithm is equal to the base of a power inside the argument here, then the answer is always just going to be the exponent. Part E says the natural log of 1 over the square root of e. Okay, here. So the base here on the natural logarithm again is e, and the question is asking for what is the exponent so that I could get 1 over the square root of e. Let's try to type that in there. There we go. So in order to really answer this, I think I'm going to rewrite this a little bit. Instead of writing it as the square root of e in the denominator here, I'm going to write it as e to the 1/2 power. Anytime you've got the square root of a number, that's equivalent to saying that it's raised to the 1/2 power. And so we can see then that this is going to be e to the power of negative 1/2. All right, so this is going to be negative 1/2. For part F, we've got log base 16 of the cube root of 16. So this is another case where I'm going to try to rewrite the root as an exponent, a fractional or a rational exponent. So the cube root of 16 is equivalent to saying 16 to the 1/3 power. And so just like we saw in part D, when we've got the base is the same as the base of a power in the argument, that our answer here is going to be whatever that power is, or that exponent. So in this case, this is going to be 1/3. Part G says log base 2 of 32. So this is going to be very similar to part A here. Took me a second to think about 2 to what power 64. This one's not going to take as long. It's going to be 2 to the 5th power is 32. So log base 2 of 32 is going to be 5. Log base 4 of 8. Now we're getting a little trickier here. Okay, since 4 to what power is 8? Now 8 is not a power of 4 in the sense that you can't raise 4 to a whole number power and get 8. Right? 4 to the first power is 4. 4 squared is 16, so it's got to be somewhere in between there. A strategy you can use here is to say, okay, well, let's actually call this x. And let's rewrite both sides of this equation as powers of 2. So 2 to the 2nd power, that's the same thing as 4, right? 2 squared is 4. And 8 is the same thing as 2 cubed. Now, if I raise a power to a power, like I'm doing on the left-hand side here, I can multiply those powers to combine them. So what I've got here is 2 to the power of 2x is equal to 2 to the 3rd power, 2 cubed. And so now I've got a statement where 2 to the 2x is equal to 2 to the 3rd power. Here, since both of my bases are the same, I can, yep, you guessed it, drop the bases, and we get 2x equals 3. I don't know why I really like saying that. So here we can divide both sides by 2 and see that x is going to be 3/2. So in conclusion here, 4 to the 3/2 power is 8. So log base 4 of 8 is 3/2. Number 4, we are expanding the logarithms. So we want to rewrite these. And it says your final answer should have no exponents, so we'll also rewrite those exponents as coefficients when we get there. So first, we're going to use that product property to split this up as log base 9 of q to the power of 0.6, kind of a weird one, plus log base 9 of r to the 0.4 power, 4/10. Now it says your final answer should have no exponents, so we need to deal with these. And we can do that by rewriting this so that this number right here is actually a coefficient of the logarithm. So let's see, the best way to do this is probably going to be just copy and paste, and then move these exponents out to the front. Now you can go back to the notes or the homework video. I go in a lot more detail on like the names of these properties. But since this is just review, I'm just going to kind of walk you through the correct steps here. So there you go. We've expanded this as much as we can. Part B, we've got a quotient here, so we are going to split these logarithms up using subtraction rather than addition like we did in part A. So I can rewrite this as, oh, it's another base 9. Okay, so I'm just going to steal this. Log base 9 of r cubed minus log base 9 of q to the 6th. And just like in the last problem, we can rewrite this with no exponents by taking those exponents and moving them over to be the coefficients of each individual logarithm. So here I'm going to change, I'm going to move this exponent of 3 out to be the coefficient of the log, and this exponent of 6 I can move over here. Okay, well, that's the end of the first page. Let's take a look at the next one. Number 5 says condense the expressions so that you write them using a single logarithm. So we're going to try to combine these using the properties of logarithms. This first one, we're going to use the product property to combine these two logarithms. So we can rewrite this as log base 2 of 1 over x times 1 over x squared. Oh, my 2. There we go. Okay. So we can actually combine these. 1 times 1 is 1. X times x squared is going to be x cubed. And so we're going to end up with 1 over x cubed. You could rewrite this. I mean, this answer right here is fine, but you might see it written with a negative exponent. So just in case you run across one that does have a negative exponent, we can say that this is also equal to x to the negative third power. Either one of these two answers are fine, but I'm going to go with the one without the fraction. B is kind of similar. We're going to use the properties once again. But this one we have to use two different properties. We're going to move these coefficients to be exponents of the argument of the logarithm using that power property. So first I'm going to rewrite this as log, natural log of 6 cubed minus natural log of 3 squared. Now 6 cubed is 216, 3 squared is 9, so we've got natural log of 216, not 261, minus the natural log of 9. And so we can rewrite this using a quotient, using that quotient property, 216 divided by 9. I'm trying to think, is that something that we can simplify? Yeah, see, 9 goes into 21 2 times, so 36. So yeah, we can actually, that divides evenly. So let's write this as the natural log of 24. Number 6, now we're getting into solving equations. So basically when you're solving equations, they kind of fall into two categories. These logarithmic and exponential equations. One category would be like if you get the bases on both sides to be the same, then you could drop the bases in the case of an exponential equation, or drop the logarithms if they have the same base. Or if you end up with just a logarithm on one side, then you want to rewrite it, if you have a logarithmic equation, you want to rewrite it as an exponential one and vice versa. So as we go through here, we'll kind of just, I'll want to categorize each one of these equations so that you start to get a better feel for how to approach them. So 6a, it looks like we've got 2 powers of 3 kind of disguised here. I'm going to rewrite both of these sides as powers of 3. So 1/3 I can rewrite as 3 to the negative 1. And 81 is going to be 3 to the 4th power. So whenever you raise a power to a power, you're going to multiply your powers. And really what I'm trying to do here is just rewrite the equation so I have the same base on both sides. That way I can drop the two bases. So now I can use the property, the one-to-one property, to say that, well, if 3 to something is equal to 3 to something else, then the two exponents have to be equal to each other. So from here I can say that negative x plus 2 is equal to 4. And I can subtract 2 on both sides to get negative x equals negative 2. And then divide both sides by, oh wait, careful, Mr. Schuler, that should be positive 2. Divide both sides by negative 1 here to get negative 2. All right, part B. Again, we've got two numbers that, right off the bat, the bases are not the same, but we can force them to be the same since they're both powers of 2. So I'm going to rewrite 8 as 2 cubed. And I'm going to rewrite 4 as 2 squared. So I'm kind of slowly making my way to where I can write both of them as powers of 2, and then I can drop the 2's. We've got x squared minus 3 up here. Now in both of these, we're raising a power to a power. So just like on part A where we had to multiply our powers, we're going to do that here. So 2 cubed to the x is going to be 2 to the power of 3x. And then we need to multiply 2 by x squared minus 3. So really I need to distribute that 2 there. So I'll get 2x squared minus 6. Now I'm at a point where I can drop the bases because I notice that they are the same. And I can set 3x equal to 2x squared minus 6. And now I've got a quadratic equation. So before it kind of devolved into a linear equation on part A. Here we got a quadratic here. And with quadratic equations, you always need them to be equal to 0. So I'm going to subtract 3x on both sides. And I'm going to write this in standard form here. And I want to think, try to think whether or not this is factorable. Kind of thinking maybe it's not. When you have to solve a quadratic, you really have, there's more than 2 options, but I like to just kind of focus on the 2 main options here, which is factor it if you can, and if you can't, then go ahead and use quadratic formula. So let's see here. In order for this to be factorable, I need 2 numbers that multiply to give me negative 12, but add up to negative 3. And if there aren't 2 numbers that do that, then I'm stuck using the quadratic formula. So let me just think on this here for a second. My factors of 12 are going to be 1 and 12. No, those don't have a difference of 3. 2 and 6. No, that's a difference of 4. 3 and 4. So yeah, so this is not going to be factorable. Maybe I'll make a little note here. Okay, so it's not factorable. So since it's not factorable, we need to use the quadratic formula. So the quadratic formula, I'm going to read it with, and kind of say A, B, and C, but as I say A, B, and C, I'm going to be plugging in 2 for A, negative 3 for B, and negative 6 for C. So x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. So it looks like we've got 2 solutions here. Let's make sure they're real, and I think they are, yeah, because this is going to be positive and a negative times a negative. So yeah, we're going to get 2 real solutions. They'll just be irrational. So let's go ahead and simplify this. Negative 3 is just going to be positive 3. 3 squared is going to be 9. And then we've got 4 times 2 times 6. 4 times 2 is 8, so let's just change that to 8. So negative 8 times negative 6 is going to be positive 48. And then 2 times 2 is 4. I'm kind of simplifying this one little piece at a time. 9 and 48 is 57. And yeah, that's going to be irrational, so I'm just going to go ahead and leave my solutions like this. Part C, we want to approach it the same way we did A and B, where we try to write both sides of the equation using the same base. Here, though, we've got 2 to the x times 8 to the power of negative x equals 4 to the x. So I'm going to go through and just rewrite all of those, the 8 to the negative x and the 4 to the x, write them all as powers of 2. So 8 is 2 cubed, and then 4 is 2 squared. Whenever I raise a power to a power, just like in the last couple problems, you're going to make sure to multiply those powers. So 2x times 2 to the power of negative 3x equals 2 to the power of 2x. Now over here, I've got 2 to the x times 2 to the negative 3x. I'm multiplying two powers with the same base, and the way to do that is you're going to add the exponents together to combine them. Okay, so this left-hand side is going to end up being 2 to the power of x plus negative 3x, or x minus 3x. So now that I have both sides written as simply powers of 2, I can drop the bases and set the exponents equal to each other. So x minus 3x is going to be equal to 2x. I guess I could have simplified this, right? Kind of going back here, x minus 3x is negative 2x. So, well, this is kind of interesting. What do we need to do here? We need to subtract 2x from both sides. It's going to give me negative 4x equals 0. And then if I divide both sides by negative 4, I'm going to get x equals 0. So a little not very climatic here. Yeah, this is going to be 0, and I guess that this would be a really easy one to check because anything to the 0's power is 1. So essentially we have 1 times 1 equals 1, which is true. All right, there's letter C. Let's move on to D. So now we've got some equations where we don't have like the same power on both sides. At 10 and 57, we're going to run into trouble if we try to write both of those as powers of the same base. So in this case, when you just have, when you can't do that, and you just have the variable in one of the exponents, what we want to do is rewrite this as a logarithm. So remember that a logarithm is just an exponent, so our logarithm should equal 2x here. The way we're going to write this is log, and then the base is 10, so I'm going to erase this, but just kind of to temporarily kind of show you where everything is coming from. Log base 10 is coming from right here, this base. That is our common log, so I am going to erase it, but I just kind of want to show you in general where all these pieces go, right? So the base is the base in both cases. The argument of the logarithm is the power here, and then since a logarithm is the exponent, that's the 2x. So now typically with your common log, you're not going to write 10 here, so I'm just going to delete that. So log 57 equals 2x, and if I divide both sides by 2, I'm going to end up with x equals log of 57 divided by 2. This top number is irrational. It'd be like if we had the square root of 57. There's nothing really we can do to simplify that further, so we're just going to leave that alone, and there's our answer. Letter E. Looks like we have just a single, I want to kind of point out how D and E and, well, even F are going to be different from A, B, and C. A, B, and C, you can write both sides of the equation as powers of the same base, and down here you can't really do that. 39 is not going to be a power of anything. So what we're going to do here is we're going to just start by dividing both sides by 2. 10 to the power of r minus 1 equals 39 halves. And just like with part D, problem D here, we want to rewrite this as a logarithm. So again, it would be log base 10. This time I'm not even going to bother to write the 10 since I kind of showed you that on the last one. So we have log of 39 halves, which is going to be some irrational number, equals r minus 1. And then from there, all we need to do is add 1 to both sides. So I get r equals log of 39 over 2 plus 1. Sometimes your answer is going to look like this. They're not very satisfying, I don't think, but that's just what they look like. Yeah, that's just going to be our answer there. And if you could write this as a decimal, I guess. It'd be 19.5, but there's really no reason to do that. You can just leave it as a fraction. Letter F. We will start this problem by subtracting 3 on both sides. So I'm going to get 4e to the power of n plus 2 equals 42. Then I'm going to divide both sides by 2. Again, I don't get this clean division. Geez, who wrote these problems? Oh, wait. 42 over 2. Now, I can reduce this because both of these are even. Oh, wait, I'm sorry. 42 over 4. Yeah, I could still reduce it. I guess I was just getting a little ahead of myself there. They're still divisible by 2. They're both even. So this could be simplified to be 21 over 2. And now that we've got an exponential equation where we just have really just one power here, and we're not going to be able to write this as a power of e, so we're going to rewrite this as a logarithm. We're going to have the natural log, which is log base e, or base Euler's number, of 21 over 2 equals n plus 2. And so to isolate n, I just need to subtract 2 from both sides. So I get n equals the natural log of 21 over 2 minus 2. And I think that about wraps it up for page 2. Yeah. Okay, so let's move on to page 3. Looks like we've got some more solving to do here. 7a will start by dividing both sides by 2. That'll leave me with the natural log of 4x equals 15 over 2. Now I want to rewrite this as an exponential equation. So kind of doing the opposite of what we did up here in number 6 with these exponential equations. We rewrote them as logarithms to isolate the variable. Here we want to kind of go the other way where we rewrite the logarithm as an exponential equation. So the base here is Euler's number e. The exponent, remember the logarithm is the exponent. So the exponent here is 15 halves. Or if you prefer decimals, I guess you could write it as 7.5 equals 4x. And then to isolate x, we need to divide both sides by 4. And there you go. Again, kind of a weird looking answer here, but there's really not much we can do to simplify that. Letter B, we've got the natural log of root x plus 1 equals 2. This is already set up to where I've got a single logarithm isolated. So I'm just going to jump straight to the conversion here where I convert this into an exponential equation. So again, my base is e, because I've got the natural log here. So e to the power of 2 is the square root of x plus 1. Now here I just want to make sure that when I solve this, that I do a little domain check, make sure I'm not getting like a number that is going to be imaginary or anything. So just when we solve this, we'll keep an eye out for that. So here I need to square both sides to get rid of that square root. So it's going to give me e to the 4th equals x plus 1. Then if I subtract 1 from both sides, I'm going to get x equals e to the 4th minus 1. And yeah, this is going to, if I plug this in here, it's going to be positive, so I don't have to worry about any extraneous solutions or anything like that. So yeah, I get e to the 4th equals 1. Wow. What a great answer. Okay here. Yeah, so letter C. We've got log base 8 of x minus 1 equals log. Okay, so we've got a couple different logs here. What we're going to have to do here is we are going to be able to use the 1-to-1 property and cancel out the log base 8s, but before we can do that, we need to combine these two logarithms. And we can do that since we're subtracting the two logarithms and they have the same base. We can combine them by dividing the two arguments. We have log base 8. Oops. Where's my base button? There we go. Log base 8 of x minus 1 equals log base 8 of x minus 2 over x plus 2. And so now I can drop those logarithms and just set the arguments equal to each other. So here I'm going to have x minus 1 equals, we're going to have a little bit of a, we're going to have to practice our algebra here. Oh, geez. Okay, so we're trying to solve for x here. Don't really want those fractions in there, so what I'm going to do is I'm going to multiply x plus 2 on both sides of the equation. So you get x minus 1 times x plus 2 equals x minus 2. And this is going to end up being a quadratic, so I need to have it equal to 0. To get it there, I'm going to FOIL these two. I'm going to multiply these two binomials together. So let's just do that first. X times x is x squared. X times 2 is going to be 2x. Negative 1 times x is negative x. And then finally, negative 1 times 2 is going to be negative 2. I can combine these two like terms here, the 2x minus x into just x. And so that's the quadratic trinomial I get when I multiply these two binomials. And it equals x minus 2. So like I was saying before, and like we've seen on some previous problems, when we're solving a quadratic, we do need to have it equal to 0 so that we can either factor or use the quadratic formula. Actually, this is actually going. We actually will not need to use either one of those, because check this out. Oh, I didn't even catch this, but look, if I subtract x from both sides, both of these are going to get canceled out. And if I add 2 to both sides, both of these are going to cancel out. So when I'm going to go ahead and do both of those at the same time. I'm going to subtract x and add 2 to both sides, and I just am left with x squared equals 0. So I take the square root of both sides, I get plus or minus 0, which are both the same number. I get x equals 0 here, but before I box this, I need to do a domain check, and I forgot to do that over here. I think I did it on part B. On part A, I just didn't check real quick. But basically, you got to make sure that whatever you're plugging into x doesn't cause a domain problem for the log function. So the domain for any log function is gonna be all the positive numbers. So if you plug something in and this becomes either negative or 0, then we have an extraneous solution. Now this number down here is a positive number, so if I multiply that by 4, it's still positive, so I really didn't have to worry about that. But here, if I plug in 0, it doesn't really cause any problems on this right-hand logarithm, but if I plug in 0 into either this one or this one, notice I get like negative 1 or negative 2, I get a negative number inside both of these logarithms, and that's a problem. It's going to cause a domain issue, a domain error, if you will. So, unfortunately, yeah, we're going to have to say that this solution right here is actually not a solution. It's an imposter. Okay? It is what we call an extraneous solution. And since we don't have any other solutions to check, that was really the only one, then unfortunately, in this case, we're going to say that there is no solution. No answer to this one. A little bit of a bummer there, but it is what it is. Okay, so there's C. Let's move on. D. Okay, so this one is set up sort of like a quadratic here, and I'm going to just kind of work out a similar quadratic off to the side so you can see how this is going to be similar. So if I had something like U, what happened here? So out to the side, U squared plus U minus 2 equals 0. This is something that's pretty easily factorable. what we would get is two numbers that multiply to give me -2, but add up to +1. Let me move this over so you can actually see it. Is that better? Yeah, I think that's better. I'll scoot this over as well. Oh, doesn't want to let me scoot it over. Just delete it. Okay, so we can factor this as u minus 1 times u plus 2 equals 0. And this would result in u either being 1 or u being -2, right? Okay, so this is like a similar problem here. It's just instead of u, we've got 3 to the x. So this is really like, and maybe I can rewrite this just so you can see how it actually is that. The 2x, if that's throwing you off, that's just because when you raise a power to a power, you multiply your powers. So just to kind of show you what's really happening here. Hold up. What's going on here? Let's try that again. 3 to the x squared plus 3 to the x minus 2. You can see how if I rewrite it like this, it becomes a little bit more obvious that it is the same essential setup as u squared plus u plus or minus 2 equals 0. So when I factor this, I'm going to get, instead of u, I've got this 3 to the x, so 3 to the x minus 1 times 3 to the x plus 2 equals 0. Let's kind of line these up so you can see which steps sort of correlate to which ones here. Let's see, move this over a little bit, just make this a little easier to read. Okay. So now if I set each one of these factors equal to 0 and solve, I'm going to get 3 to the x equals 1, and 3 to the x equals -2. Notice these are the same two numbers on the right-hand side that I got over here. Now, since we have 3 to the x and not just x, I do need to continue solving this. I'm not quite done here because I need to figure out what x is. So for each one of these, I am going to rewrite this as a logarithm. Now right away I can tell that I'm going to get I'm not going to get a solution out of this factor over to the right, because there's no x value that if I raise 3 to that power, it gives me any negative number. This is going to be outside of the range of an exponential function. So this one does not produce any solutions over here on the right. But the one on the left we shouldn't really have any problems with. Actually, you probably don't even need to convert it. 3 to what power is 1? Well, 3 to the 0th power is 1. If you wanted to rewrite it, you could rewrite it as log base 3 of 1, but that's just going to equal 0 anyway. So yeah, we get x equals 0. So you can kind of section this off so you can kind of see that that's a little different. Okay, for letter E, it's kind of the same setup as letter D. So the only difference I see here is this +1, what's going on there. And so I'll kind of show you how we can rewrite that. So that first term I can rewrite as 3 to the x squared. So that's basically going to be the same thing as letter D. But this x plus 1 is kind of funky here, right? We've got 3 to the x plus 1, but remember that when you multiply two powers that have the same base, you add the exponents. So I could rewrite this as like 3 to the first times 3 to the x, right? And then 1 plus x would be x plus 1. So we have -4 equals 0. So I want you to think about this as being like u squared plus 3u minus 4. Okay, I'm not going to write it out just because I'm kind of running out of room here. And the concept we kind of went over in part D. But ultimately we're going to factor this as 3 to the x plus 4 times 3 to the x minus 1. Right, if these were u's, it'd be like u plus 4 times u minus 1. Now I can set each one of these equal to 0 and solve them if they can be solved. A lot of times you get these equations that actually cannot be solved. So here I have 3 to the x plus 4 equals 0, or 3 to the x minus 1 equals 0. So 3 to the x is going to be negative 4 in this case, and we can tell that is not going to work out. Over here we can, if we add 1, we get 3 to the x equals 1. Okay, so we have a range error over here. 3 to the x can never equal negative 4, so let's just go ahead and x that one out. That one cannot be a solution. And then 3 to the x equals 1, the only thing x could be there would be 0. So we actually get the same answer for E that we did for D. Fun stuff. Yeah, all right, good. Okay, so we got x equals 0 for both of those. Kind of lame, but whatever. All right, for letter F. Now we're getting kind of weird here. So we've got two powers, but the bases are not the same, and they're not powers of each other. So what we're going to do is we're going to use this little natural log trick to move this exponent down to be a coefficient so we can actually work with it. So I'm going to take the natural log of both sides, and you can actually do this with any base. It does not have to be the natural log. I just prefer natural log personally, just because it's less writing. Okay, it takes the fewest number of characters to write natural log versus any other base. But you could just use common log. You could use log base 5 if you want. Some people you'll see will use like log base 3 or log base 4, and that does simplify the final answer a tiny bit, but not really enough to make it worth, trying to figure out what base to use every time. So I just use natural log every time. And we can use this power property to rewrite this as 1 minus 2x times, I guess that should really be in parentheses here, times the natural log of 3. And this is going to get a little crazy here, but equals x times the natural log of 4. Okay, so from here, I'm trying to isolate x, so what I need to do is get all my terms that have x on one side and the terms that don't have x on the other side. So what I'll do first here is distribute this natural log of 3 is really just a single number. Okay, it's irrational, but it's like square root of 3. It's just a number. I'm going to distribute that to both of these terms. That's going to give me the natural log of 3. Oh, switched over to blue all of a sudden. There we go. Natural log of 3 minus 2 natural log of 3x equals, I'm actually going to rewrite this as natural log of 4 times x because I really want to emphasize that that's really just a coefficient. Okay. So I'm going to try to get my x's on the same side, and I guess the easiest way to do that would be to add this 2 natural log of 3x over to the right-hand side. Plus 2 natural log of 3x. There we go. Okay, now what we need to do is we need to factor out the x as a GCF. And then once we do that, we can divide whatever is left over back on the left-hand side, and we'll have our answer. So I'm going to factor out that x. It's going to leave me with the natural log of 4 plus 2 times the natural log of 3 on the right-hand side. And then my final step here is going to be to divide by this number. And really, this is just a single number. All these are constants. There's no variables in here. So it's just going to be some irrational number. And so we're just going to divide that on both sides here. So we'll get our final answer. x equals the natural log of 3 over the natural log of 4 plus 2 times the natural log of 3. Now, if you used a different base, nothing's really going to change in terms of the algebra here. It's just that your final answer will have a logarithm with a different base, but it really shouldn't matter what base you use. I will just, on these kind of problems, always use natural log. It's just a personal thing. It's the one I like the best, but you can use any one you want. G. Okay, this is kind of the same type of problem as F, where our bases are not the same. So we're going to have to work it out basically exactly the same way we did this one. Okay? In fact, it's so similar that I'm just going to copy and paste my work here and just change everything that is different. So, to take the natural log of both sides, so I have e to the x plus 3 equals natural log of pi to the x. Right? And then I'm going to use that power property to bring the x out to the side. Okay, so I should have x plus 3 here. And here I have the natural log of e, which actually does, this is going to simplify a little easier actually, because this natural log of 3, let me go ahead and just delete the rest of this, because this one actually works out a little easier than the last one. Only because the natural log of e is just 1. So I actually don't need to distribute here. This is just going to be x plus 3 equals x times the natural log of pi. So now I'm going to move my x's to the same side. So I guess I'll just subtract x over here on both sides, and I'll get 3 equals the natural log of pi times x, just using a little what is it called, the commutative property here to rearrange those terms. And then I have minus x. Now I can factor out the x on both of those terms as a GCF here. So I get 3 equals x times the natural log of pi minus 1. And then to finally get x, I need to divide both sides by natural log of pi minus 1. So my final answer here is going to be 3 divided by that, natural log of pi minus 1. All right, yeah, just looking over this, making sure it looks good. I think we're good there. All right, letter H. We've got a log on both sides, but we've got that pesky coefficient of a 2 in front of the log x on the right-hand side. So I'm going to rewrite this so that that's an exponent. Now I can drop both logarithms. And so I've got a quadratic here. I need to set it equal to 0. So I'm going to move everything to the right-hand side to, really I just want to make sure that leading coefficient's positive. Just makes it a little bit easier to think about the factors. So we've got minus 7x plus 12. And two numbers that multiply to give me 12 but add up to negative 7 will be negative 3 and negative 4. So I can factor this as x minus 3 times x minus 4. So that's going to give me two solutions here. X equals 3 or x equals 4. And so let's do a little domain check here on the logarithm. If I plug in 3, 3 times 7 is going to be 21. It's going to be positive. This one's going to be positive, so no problem there. If I plug in 4, yeah, it's even going to be more positive. So this one actually does have two solutions. So I think maybe just to clean this up a little bit, I'll write x equals 3 or x equals 4. Letter I. Both of these are powers of 3, so I don't have to go through this whole natural log business. I'm just going to rewrite both of these as powers of 3. We got 3 squared to the power of 2x equals 3 cubed to the power of 3x minus 4. So whenever I raise a power to a power, I need to multiply my powers. So I'm going to get 3 to the power of 4x equals 3 to the power of, and I need to distribute that 3, so that'd be 9x minus 12. Now I can drop the bases, and I'll set 4x equal to be 9x minus 12. I can subtract 9x from both sides, give me negative 5x equals negative 12. And then finally I can divide both sides by negative 5, and my answer is going to be 12/5. Notice I'm not doing a domain check on the exponential equations, and that's because exponential equations have a domain of all real numbers. So you really do not need to do a domain check on those. Okay, well, that was a pretty beefy page 3. Geez, these are probably going to be the harder questions that we have. Let's take a look at page 4. Number 8a has the log of 7x minus 12 equals 2 times the log of x. So we want to use the one-to-one property here to cancel out those logs, but before we can do that, we need to take care of this little coefficient here, this 2. So we're going to use the power property to rewrite this as log of 7x minus 12 equals log of x squared. And so now we can cancel out these logs. We'll be left with 7x minus 12 equals x squared. And now we have a nice little, not exponential, but a quadratic equation that we need to solve. So what we need to do to solve a quadratic is we need to set it equal to 0 so that we can use either the quadratic formula or factoring. And I prefer factoring just because for me it's a little bit easier. Especially when the leading coefficient is 1 here. And so I'm trying to think of two numbers that multiply to give me 12 but add up to negative 7. Those are going to be negative 3 and negative 4. And so if we set each one of these equal to 0 using the zero product property, we can see that if x minus 3 is equal to 0, then x is going to equal 3. And similarly, x could equal 4. We do need to do a little domain check here, like with all these log problems, to make sure we don't get an extraneous solution. If I plug in 3 here, I get 12 minus 12. Okay? We cannot take the log of 0 here. So that means that x equals 3 is going to be, you guessed it, extraneous. And if we plug in x equals 4, we get 28 minus 12. That's going to be positive, so that is going to be a solution to the equation, and it'll be the only solution to the equation. Oh, wait a minute. Hold up here. Just hold up here. 7 times 3 is not 12. What am I talking about? 7 times 3 is 21. A little bit too quick to jump to an extraneous solution here. Yeah, my arithmetic skills need a little bit of work. This one is going to be a safe solution here. So yeah, we do get 2 solutions here. Yeah, I don't know what I was thinking that it equals 12. I guess I was just thinking 3 times 4 for some reason. I don't know. I cannot really tell you what was going on in my head there. Part B. We've got log base 2 of y plus 1 equals 3 plus the log base 2 of y minus 6. So what we need to do first is we need to subtract that log base 2 of y minus 6 on both sides so that we can get our logs on one side and we'll get the constant on the other. So I'll have this log of y plus 1 minus the log base 2 of y minus 6 equals 3. And so now I can use my quotient property here to combine these two logarithms, y plus 1 over y minus 6. That's going to equal 3. And so from here I can use the inverse property to rewrite this as an exponential equation. 2 cubed equals y plus 1 over y minus 6. I'm going to have to squeeze this in. I'm afraid I'm going to run out of room here. So I'm going to move this stuff up a little bit. We'll try to, no, maybe center justifies the way to go here. Okay, so now I'm trying to isolate this y. So what I need to do is I need to multiply both sides by this y minus 6 to move it over here. 2 cubed is 8, so I'll just go ahead and simplify that at the moment. And I get 8 times y minus 6 equals y plus 1. Using the distributive property, I can say that the left-hand side can be 8y minus 6 times 8, which is 48. And now I can start moving things around. So for instance, I can subtract y on both sides. And just for the sake of not running out of room, I'm going to add 48 to both sides and just kind of do this both in the same step. And I get 7y equals 49. When I divide both sides by 7, I get y equals 7. Let's do a quick little domain check here. Make sure we don't end up with a 0 or a negative inside any of the logarithms. 7 plus 1 is positive, so that checks out okay. 7 minus 6 is also positive, so no domain problems here. Letter C is going to be one where we have to invert the equation and rewrite it as an exponential equation. So whenever you don't see the base of the logarithm, it is assumed to be 10. So I'll have 10 to the power of 2 equals 3x plus 1. 10 squared is 100. Go ahead and simplify that right off the bat. And then I'm going to subtract 1 from either side to give me 99 equals 3x. And if I divide both of those sides by 3, I get x equals 33. And that number is a pretty big, well, relatively anyways, positive number. So if I plug this in here, I won't run into any domain issues. Let's go down to letter D. Ooh, this one's kind of funky. Log base 3 of log base 5 of x equals 1. Oh man, so I think what I'm going to do here is I'm going to rewrite this as an exponential. 3 to the first power equals log base 5. Where's my base there? There we go, log base 5 of x. 3 to the first power equals whatever is in here. Now, I still need to get this x by itself, so what I'm going to have to do here, and I'm going to have to, well, I'm going to have to go back to, I'm going to have to do it again. I'm going to have to invert this again to isolate that x. So 5 to the power of 3 is equal to x. So 5 cubed is, well, let's think about this. 5 times 5 is 25, times 5 is 125. 5 times the natural log of what we got? 3x over 4 equals 12. And I'll start this by dividing both sides by 5. And then since I've got a logarithm only on one side, I need to use that inverse property, rewrite this as an exponential. The natural logarithm has a base, which is Euler's number, e. So e to the power of 2/5. Ugh, got a nice little root going there, equals 3x over 4. And so now I'm just going to, isolate x here. I need to multiply by 4. I don't want to retype all that. I'm going to multiply by 4 on both sides, and then divide everything by 3. What a nice answer that is. Yeah. You could write this using roots. I don't think there's any real particular advantage to doing that. What I mean by that is you could write this little e to the 2/5 power as the fifth root of e squared. But again, there's not really an advantage to doing that. In fact, when you get to calculus, you're going to find you're going to be better off leaving your radicals as rational exponents anyway. So it's good to just kind of stay in that habit of just leaving it as a fractional exponent. Okay, well then, that one was pretty fun. Let's try the next one. Looks like we need to take care of this coefficient up front on letter F here. We have the natural log of 5x plus the natural log of x to the fourth. Is that right? I guess so. Interesting. Okay, so now I need to combine these, and I'll do that with multiplication using that product property, the natural log of, let's see, if I have 5x times x to the fourth, well, x times x to the fourth is going to be x to the fifth equals 6. And so I can rewrite this using exponents, like I did the previous problem. E to the power of 6 equals 5 times e to the fifth power. I need to divide both sides by 5. And then I need to take the fifth root of both sides, or, just like in the last problem, I was saying, you're better off with these fractional exponents rather than thinking of these as roots. The fifth root of something, a little check mark, radical symbol, we don't really need that. Instead, what I'm going to do is, raise this whole thing to the 1/5 power. Okay? So I'm going to raise this whole thing to the 1/5 power. You could write it as the fifth root, but yeah, I kind of like this better, to be honest with you. Okay, wow. Well, this is a lot of solving we just did here. Pretty intense problems, But here we've got some, we're moving on into the word problems here. Number 9, the population of Pi Town was 23,450 in 1998. The population decreased at a rate of 3.12% per year. I think we kind of missed an opportunity here. If it was Pi Town, this is 3.14. That'd be cooler. But all right, whatever. 3.12% per year. Write a function rule to model the scenario and find the population in 2018. So let's write our equation first. So our population in terms of x, or I guess let's do it in terms of time, is going to be our initial population in 1998 was 23,450 times 1 minus 0.0312 to the power of t. I do want to simplify this a little bit. So yeah, I'm going to break out the old calculator here. Gotta open it up. Let me make sure you guys can see it. Nope. Okay. There we go. Let's put it down here so you can see it a little easier. Okay, so I need to do 1 minus 0.0312, and that's going to give me my decay factor here, 0.9688. Okay, so I'm going to rewrite this function as 0.9688. All right, so now this is the function that's going to give me the population t years after 1998. Okay, so this is, let me make a note of that. This is the population t years after 1998. So if I want to find the population of the town in 2018, that's going to be 20 years later. Okay, so we're actually not going to have to solve anything here. This will be kind of nice. What we're going to do is we're going to plug in 20 into t, And we'll get our solution here. Let me scroll down so you can see what I wrote there. So the population, when t is 20, it's going to substitute 20 in here and evaluate this. This is going to be something you're really going to have to do with the calculator. So let's go ahead and type it in. 23,450 times 0.9688 to the power of 20. Now we're going to get a decimal here, and we're talking about a population, and you can't have like a tenth of a person. So we're going to round to the nearest whole number here. So I'm actually going to say this is going to be approximately, since we're rounding here, 12,440. Okay, and it's a good idea to, whenever you're answering a word problem, is to state the answer in the context that the question was asked. Instead of just leaving it like this, we'll say, the population of the town in 2018 was approximately 12,440. All right, I'm not sure if we're going to need this calculator after this problem. We might. I'll bring it back if we do, but I'm going to hide it for now. Okay, well, there's page 4. Let's move on to page 5. Number 10 says a model for the number n of people in a high school community who have heard a certain rumor is given by this formula, where P is the total population of the community, D is the number of days that has elapsed since the rumor began. In a community of 1,000 students, how many students will have heard the rumor after 3 days? Okay, so in that case, D would be 3, and we're just going to input that in the equation up here. If the population is 1,000 students, we're going to input that here. Okay, so let's see what we're doing here. We're going to have to plug all that in, I guess. N equals 1,000 times 1 minus Euler's number to the power of negative 15 hundredths, or negative 15 hundredths, times 3. And then this is just going to be a calculator problem. We're just going to type this in. So I guess I'm going to have to bring the calculator back right away. That did not take long. Actually, I think we might have a few word problems here coming up, so we're probably going to need it. So yeah, let's go ahead and type that in. What do we got here? 1,000 times 1 minus Euler's number to the power of negative 15 hundredths times 3. Okay. I forgot my close parentheses there, but I think this calculator will be able to handle that. Yeah. So it's going to be approximately 362 students. All right. So we'll say approximately 362. I'm going to make this calculator a little smaller. It seems to be getting in the way a little bit. All right, so there's our answer there. How long will it take for virtually everyone to hear the rumor? Okay, so, we're not going to say when does everyone hear the rumor. We're going to say when does mostly everyone hear the rumor. So think we have a little bit of leeway as far as how we want to answer this question, because I don't think this will ever get to 1,000, but it'll get pretty close. So I think what we'll say is, how about when we get to 999? That would be virtually everyone. So 999 equals 1,000 times 1 minus e to the power of negative 1,500ths times d. And we're going to solve this for d. So, yeah, and you'll see, like, if I did 1,000 here, we would run into a problem solving-wise. Dividing by 1,000 would get me 1, and then subtracting 1 would get me 0. But this function's never actually going to get to 0. So not everyone's going to hear the rumor. That would be, we might get to a point where it kind of rounds to that. Virtually everyone. I wonder, since it's not actually going to get to 1,000, I think we might be better off if we say, okay, if we actually want it to be everyone, or approximately everyone, we would need to round. So this would be the minimum number that we would want to get, because this would round to 1,000. I think we're going to actually do 999.5 here. Okay, so first we're going to divide both sides by 1,000. I'm not going to use the calculator until the very end here. Okay, so this would be 0.9995. So I'm going to have to scroll down a little bit here. Give myself a little bit more space. All right, so now I want to subtract 1 from either side. So if I do 0.9995 minus 1, it's going to be like 0.0005, but just, okay, wow, it's given, I don't know why is it giving the answer to me in scientific notation? That is bizarre. I mean, it could display that number. Is my mode? What's going on with my mode? Yeah, that's kind of interesting there. You don't really need a calculator for that anyway. I said I wasn't going to use one, and then I went back on it right away. But anyway, if you subtract 1 from both sides, you're going to get 0.0005 equals negative, yeah, e to the power of negative 0.5d. And then you could divide both sides by -1 to make this positive. This would be a pretty easy step there. Okay, now we're ready to use the inverse property to rewrite this equation as a logarithm. So we've got the log base e, which is the natural log of 0.0005, oh, almost missed a 0 there, equals negative 15d. And then if I divide both sides by negative 15, I'm going to get d equals, so this is the number of days, is going to equal the natural log of 0.0005 divided by not negative 15, I lost a decimal along the way here, negative point. There we go. 0.15. Okay, so now I'm ready to use the calculator. I'm going to do the natural log of 0.0005 divided by negative 0.15. So I get about 51 days. Yep. So D is approximately 51. And then again, we want to make sure we're answering this question within the context that it was asked. So we're going to write like a complete sentence here to answer the question. How long will it take for virtually everyone to hear the rumor? Okay, it will take approximately 51 days until everyone here's the rumor. I guess I should say virtually because we are rounding here, so there's a little bit of wiggle room. And there's our answer. This one's kind of weird, you know. This whole virtually everyone thing, you know, that's a little bit vague here. I'm kind of interpreting what that means. I don't think I'm going to give you one that's worded this vaguely on the tests, so don't like freak out about that. I think any question I give you on the test will be more that'll be more well defined. So as long as you just are focusing on the algebra here, you're going to be in good shape. Okay, well that was the rumor problem. It's kind of fun, yeah. 51 days. Gosh, word travels fast. Okay, number 11. It says in 1996 there were 2,573 computer security incidents. During the next 7 years, the number of incidents increased by about 92% per year. Using the model, I guess we have to create the model. The equation is what it's referring to. How many computer security incidents were there in 2012? So let's write our equation. I'm going to use C for computer security incidents, T for time, and it's going to equal the initial amount, which is 2,573, times 1 plus, because it's increasing by 92%, to the power of T, where T is in years, years since 1996. So just to make a brief statement here, clarifying what this equation is talking about. This is the number of security incidents T years since 1996. It says, you know what, before we go further, let's simplify this. 1 plus 0.92, we can clean that up, just 1.92. So it says, how many computer security incidents were there in 2012? So in 2012, let's see, that'd be 4 and 12 would be, 16? 16 years, is that right? Let's see, 4 and 12, yeah, sorry, 16. So we want T to be 16 here, 16 years since 1996. C of 16 is going to equal 2,573 times 0.192 to the power of T. And up to the power of T, well, T is 16. So we don't even have to work backwards. There's not an equation to solve. We just need to evaluate this. And once again, we'll use the calculator to do that. So let's pull that calculator up. So definitely be a calculator problem. I'm going to make you multiply by 1.92 16 times. That would be pretty ridiculous. 2,573 times 1.92 to the power of 16. Oh boy, we're going to have to hire some security experts here. That is quite the number there. Oops. Oh, all right. Well, let's write it out. Okay, so C of 16, or the number of computer security incidents, 16 years after 1996, would be approximately, again, we're rounding here, so that's why we use the approximate symbol. Oh, without the commas, it's hard to read that number, isn't it? I'm just going to write out the number, throw in the commas, and then read it afterwards. Make sure I'm not missing a number here, 87752,489. Okay, let's throw in some commas just to make this a little easier to read. Okay, 87,752,489. Wow. Okay. So let's answer the question as a complete sentence here. we're going to say that there were, well, 87,752,489 computer security incidents in 2012. All right, we are making some progress here. Okay, well, there's number 11, and that wraps up page 5. So let's go ahead and start page 6 with some more word problems here, some more applications. Number 12, the value of the truck, or a truck, decreases 18% each year. The current value of the truck is $52,000. So part A wants us to write an exponential function that models the value of the truck t years from now. So we're writing a function v in terms of t. And our initial amount, or at least the current value, is going to be $52,000. So that's going to be our y-intercept here, our initial value. And we're decreasing, the value is decreasing by 18% per year. So we're going to do 1 minus, and then 18% as a decimal is 0.18 or 18 hundredths. Raised to the value, raised to the power of t, where t represents the number of years. Part B says use the function you wrote to find the value of the truck 3 years from now. So we're just going to substitute in, we're going to take this equation, substitute in 3, and just use our calculator to evaluate this. Let me go ahead and pull up that calculator back. There we go. All right, so we're just going to type this in. Go ahead and type in 52,000 times 1 minus 0.18. You may have simplified that to just 0.82, which would be totally fine. To the power of 3. Here we go. All right, so this should be the value of the truck 3 years from now is going to be $28,671, and I guess we'll round this to 14 cents. So if we're going to answer this question in the context that it was asked, we would say something along the lines of 3 years from now, the truck would be worth $20,671.14. Part C says use the function you wrote again to find the value of the truck 30 months ago. Okay, 30 months ago. So what we have to do is figure out what should my t value be. So if it was 30 months ago, maybe I'll just kind of write this out as I'm thinking through it. So 30 months is the same thing as 24 months plus 6 months, right? And since a year is 12 months, 24 months would be the same thing as 2 years. And 6 months would be a half a year. 6 is half of 12, so this would be half a year. So really, 30 months is going to be the same thing as 2.5 years. So we're going to plug in, actually not 2.5 years, because it's not 30 months from now, but rather 30 months in the past. So we're going to actually use negative 2.5 as the value that we're going to plug in here. So instead of plugging in here 3, we're going to do negative 2.5. And let's go ahead and type that in. So we have 50, I guess I could just copy it from here. And the only thing I'm really changing is this 3 to negative 2.5. So we should get a number that's bigger than the current value. And yeah, there we go. We get 85,000. Let's go up. There we go. So this is going to be an approximate because we are rounding here. $85,402 and 13 cents roughly. Okay, so let's go ahead once again, answer the question within the context that was being asked. So we want to say 30 months ago, the truck was worth $85,402.13. Okay. Part C, determine how many years until the value of the truck is $20,000. Not sure why these Y's are getting cut off there. They look like V's. But anyway, so in this case, we're going to use this function. But instead of substituting in a number for t and finding v, we're going to go the other direction. We're going to substitute this value for v. So the value is going to be, there we go, $20,000. And we're going to solve for t here. We're going to do a little bit of algebra, and then we'll throw in the final computation into the calculator. So first I am going to go ahead and simplify what's inside the parentheses there. 1 minus 0.18 would be 0.82. Then I want to divide both sides by 52,000. Okay, so, and I am going to simplify this, but just to kind of show you what it looks like before the simplification. We're going to divide both sides by 52,000. So let's go ahead and simplify this. First of all, since we see each one of these has 3 zeros at the end, we can just go ahead and delete all those, divide both of these by 1,000, right? And then I notice both of these are even, so let's go ahead and divide both of these by 2. So that would be 10 over, what would that be, 26? 26, 26, 52, yeah, that checks out. They're still even, so I can do that again. So 5 over 12. And I think that's as far as we can go there. So let's go ahead and rewrite this as a logarithmic equation so that we can actually solve for t here. T is going to be equal to log base, the same base as the exponent here, 0.82, of that fraction, that 5/12. So, once again, we're going to approximate this. Okay, this is going to be an irrational number, so we're going to say t is approximately, and let's go ahead and type that in our calculator. So I'm going to hit alpha, I think it's window. Log base here, so log base 0.82. You could also, if you don't have that function on your calculator, if you're just working with a scientific calculator, you can use the change of base formula and write this as log of 5/12 over log of 0.82, and you should get the same answer. So if you don't have that function, it's okay. All right, so I get about 4.4 years, 4.112. Okay, so we'll say here, as our sort of conclusion, that after approximately 4.12 years, the value of the truck will be $20,000. Okay. All right, and that's it, I think, for page 6. All right, let's move on to page 7 here. Number 13 says the logistic growth function, written here, I'm not going to bother trying to read that, models the percent of U.S. households with cable TV, where T represents the number of years since 1980. Now, you could probably guess that this is a pretty dated question, as, yeah, I'm guessing this number is going to end up going down, which is not going to be reflected in this model. So let's see here. So since 1980, yeah. Okay, so what percent of U.S. households had cable TV in 1984? So with this function, T represents the number of years since 1980. So 1984 would be 4 years since then. So we're going to rewrite this, just write the entire equation, except instead of T, I'm going to substitute in 4. Okay, so yeah, so let's plug in 4 here. So I'm going to just change that T to a 4, and I'm going to put all this stuff in the calculator. So let's bring that calculator back up here, turn it back on. I have a big fraction here, so that I don't have to worry about parentheses, I'm going to use the fraction option in the calculator. 1 plus 484, and then we've got e to the power of negative 0.239 times 4. Yeah, this model was probably written at a time back in the day when there were more and more people getting cable TV. They probably figured, like, why would that number ever decrease? But as we've seen in recent years, more and more people are deciding to get rid of cable and kind of go the streaming route with Netflix and stuff like that. So not as many people need that much cable, the cable service. Okay, well anyway, kind of getting off track here. We get about 42.661, I guess would round to 2. Yeah. Okay, so as far as a percent goes, it's about 42, a little bit over 42%. So we're going to say, as our final answer here, in 1984, approximately 42.62% of U.S. households had cable TV. Okay, part B says, when does the model predict the percent of U.S. households with cable TV will be more than 50%? So basically what we want to do is figure out when is it equal to 50, and once we have it equal to 50, we can say it's going to be right after that. So let's go ahead and take this formula, and instead of plugging in a number for t, we're going to make this back into a t. We're going to plug this into 50%, so 50. All right, so let's go ahead and start by multiplying both sides by this denominator here. So we have 50 times all that equals 67. And so the next step I'm going to do here, you kind of have two options here. You could distribute the 50 and then kind of go from there, or you could divide both sides by 50 and go from there. Either one's probably fine. I think, what do I want to do here? I think I'm just going to divide both sides by 50. Yeah, I think that's the way to go. But if you worked it out the other way, you should still get the same answer, so don't worry about that if you're just checking your answers here. So you have 67 over 50. I don't think that's going to reduce. 50's factors are 5 and 2. I think those are the only prime factors. Yeah, so 67 is not divisible by either of those, so we're just going to leave that. So now, we don't need this parentheses anymore. We can subtract 1 from both sides. So we're going to have 67 fiftieths minus 1. And now 1 as a fraction would be 50 over 50. And 67 minus 50 is 17, so this comes out to be 17 fiftieths. All right, so now we're going to divide both sides by 1.484. This is where this number is going to get kind of out of hand here, but that's okay. I'm going to try my best to save the rounding until the very end so I can have the most accurate answer possible. So I'm going to divide both sides by 1.484. And I think multiplying that, if that's going to give me more than 3 decimal places, I'm just not even going to bother doing it here, but I'm going to go ahead and type it in just to see. 50 times 1.484. Okay, 74.2. That'll work. You could try to rewrite this as a better fraction without the decimals. It's not really necessary, though. We'll just leave it like that. And so now we're ready to rewrite this using the inverse property, to rewrite this as a logarithm. I'm going to kind of push all this up so that I can fit everything on the screen here. I'm going to have, since my base here is Euler's number, I'm going to be using the natural log to rewrite this. And so this negative, oops, not sure what happened there. Let's try this again. There we go. This negative 0.239 times t is going to equal, I don't want that to be an exponent, though. There we go. That's still giving it to me as an exponent. What's going on? There we go. Equals the natural log of 17 over 74.2. This is just going to be irrational, so I'm not even going to bother typing that in the calculator yet. Now, finally, I need to divide both sides by negative 0.239 to get my t value, and then I'll get the time. Now, this is going to be years since 1980, so we'll just make sure that we acknowledge that in our answer. So we have all this divided by negative 0.239. Okay, so let's see what that is. Now it's time to go to the calculator. Find out what we get for our it's definitely going to have to be approximate because we have an irrational number in the midst. All right, here we go. We've got a big fraction here, so I'm going to do alpha y equals, pull up this fraction here. The natural log of 17 over 74.2 over negative 0.239. I think I got that. Just kind of look at it. Yep, that looks good. And so we get approximately 6.165. All right, so that's just 3 decimal places. So in what year will it be more than 50%? So we'll just add this to 1980, and so that's going to put us somewhere in early 1986. So I'll say that in 1986, the percent of U.S. households with cable TV will be more than 50%. And let me hide this calculator so you can kind of see my whole answer there. Okay, there we go. It was just like a one problem on that page. To A, B, real quick, number 13. Okay, so let's go on to the very last page, page 8. Wow, 8 pages. Number 14. This equation models the population of Tokyo, Yokohama, Japan, where X represents the number of years since 1992. Find the population in 2018 according to the model. So how many years from 1992 to 2018? So 2018 minus 1992 is going to be 20, let's see, we got 18, or we got 8 years from here to 2008 and 18. Yeah, it's going to be 26 years. Okay, so we're going to use 26 as our value for X here. So we've got P equals 27.54 times 1.011 to the power of 26. And we can estimate the population here. Let's bring back the calculator and start typing away. 27.54 times 1.011 to the power of 26. All right, so we get approximately, now this is the p-value we're getting, so I'm going to write that first, but we need to interpret that in context, just like with all these word problems. I'm getting 36.601 as my approximate, 601. So now this population is in millions. So I think we're better off just kind of like writing it. So we're going to say, here's how we're going to write this. We're going to say, according to the model, the population in 2018 is approximately 36,601,000, and I'm actually going to go back to the calculator here real quick to look. 0.86 would round to 0.87. All right, part B says, when does the population double from 1992? So to double, we need to double the initial amount. So just as a little aside here, the initial amount was 27.54 million, and so if we multiply that by 2, let's see here, 27.54 times 2, it's going to be 55.08. So we're going to use that for our p-value and then solve for x. All right, so we're going to use 55.08 here, and change this to an x, and we're going to solve for x and then again interpret it. So first step here is going to be to divide both sides by 27.54. I should already know what that's going to happen because we know how we got that 55.08 in the first place. It's just going to be 2. Okay, so 1.011 to the power of x. Now we want to rewrite this as a logarithm. So x is going to equal log base 1.011 of 2. And we're just going to type that in the calculator to get an approximate value for x. And then we'll write our final answer here. So log base is the function we want. Log base 1.011 of 2. There we go. Okay, 63, around 63.359. And so let's try to interpret that. So it's 63 years after, what was the original one? 1992. So I'm just going to add that to 1992. You could probably do that mentally, but so in the year 2055, it's going to be when the population doubles. So the population will double from 1992 in 2055. All right, that's it for that one. Number 15 says radioactive phosphorus decay, radioactive phosphorus decays continuously at the rate of 4.95% per day. An initial amount of 5 grams of radioactive phosphorus decays after T days according to this formula. How much of the sample is left after 20 days? So we've got this formula, this A of T. That's the amount that's left in terms of time. 5 times Euler's number to the power of negative 0.0495 T. And we're saying how much of the sample is left after 20 days. This is just going to be a simple case of plugging in 20 here. This one's pretty straightforward. All right, so we're just going to type this in. No real solving involved here. Don't have to do any algebraic manipulation, no logarithms or anything. We're just going to plug the number in and hope we can use the calculator. Hopefully we don't mistype anything. So 5 times e to the power of negative 0.0495 times 20. There we go. That's really all there is to it. This one's a pretty quick one. 1.858. And, these word problems deserve a word answer. We'll say approximately, what's that so small there? Approximately 1.858 grams will be left after 20 days. And we got one last problem here. Last one. This has been a pretty long review. Hopefully you've gotten something out of it. Hopefully you're walking away from this video understanding these problems better than when you started. But let's wrap this up. It says when a living organism dies, its carbon-14 decays. The half-life is 5,730 years. How old is a wooden statue that only has 1/3 of its original carbon-14? So the formula for half-life that we're going to use here, and I'll just do it like y in terms of x, is going to be however the initial amount is. So I'll just call that A for the initial amount. So I'll use lowercase a there, times 1/2 to the power of the time divided by the length of the half-life. So the length of the half-life in this case would be 5,730. And in this case, we do not know what the original, we don't know what the original amount was. So we're just going to leave it as just like this variable. And the final amount would be 1/3 of whatever was left. Okay, and here we're going to try to solve for t. So the first thing to do is to divide both sides by a. And that's going to, dividing both sides by a here is going to cancel out both of these a's because a is divided by a is 1. And now we're ready to rewrite this as a logarithm. So we're going to say t over 5,730 equals log base 1/2, or 0.5. 0.5 might be a little bit more aesthetically pleasing here, but I'm going to just leave it as a fraction anyway. So log base 1/2 of 1/3. And then I need to multiply both sides by 5,730. Just copy all that. And then time to go to the calculator, and then we're done here. We have 5,730 log base 1/2 of 1/3.
9,081.835 years. Wow, that's pretty old. So yeah, our answer in context here, we'll say something like the wooden statue is approximately 9,081.835 years old. All right, and that wraps it up for this review. Hope you enjoyed the video. Y'all have a great day.